Awesome, welcome to chapter 7. So chapter 7 is about exponential and logarithmic functions and relations. So take a moment, read this first paragraph to yourself. Right? They play a major role in our lives. Many of the challenges we face can be exponential change. Right? Finances are the most obvious. Growth of our retirement savings, growth of student loans, how much interest we're paying on home, car, student loans, effects of inflation. Alright, so we're going to start with this exploration of exponential functions. So problem 1, characteristics of linear functions. This is back from chapter 2. Right, f of x equals mx plus b. We must respond to the following. So the variable x is the independent quantity. F of x is the dependent quantity. It's your y. The graph is a line with a slope m and a vertical intercept b. So we say it's an increasing linear function because m is greater than 0. Right, so this line is going up from left to right. Here, it's decreasing. M is less than 0. It's going down from left to right. So you will probably have to pause the video to make sure you get the full notes, but that's the beauty of YouTube and screencasts, is you can rewind as necessary. So the defining characteristic of a linear function is the rate of change. Right, the slope is constant. It doesn't change. The domain of a linear function is all real numbers. Now you can plug in any x value and we're good. And a y happens. The next example is long, but illustrates key difference between exponential functions and linear. So on December 31st around 10 p.m., you're sitting in your house watching, New Year's Eve special, and someone knocks at your door. You're like, who could be visiting, right? You go see who it is. It's a man dressed in a 3-piece suit and tie, holding a briefcase. So you open the door, right? He says he's a lawyer representing the estate of your recently deceased great uncle. Turns out he had left you money in his will, but you have to make a decision, right? You have 3 options how you're going to get your money. Option A, right? $1,000 can be deposited on December 31st, and then each day an extra 1,000 until January 31st. It's pretty cool. Immediately have money. B, 1 penny will be deposited December 31st, right? Every day the amount will be doubled until January 31st. Right, you're starting with a penny. Option C, take $30,000 on the spot. Be done with it. Given that you had been to a party earlier that night, your head's a little fuzzy. You're like, I want to think about it. So you have until 11:50 p.m. Right, so it gives you a whole hour and 50 minutes. Which option would you most likely choose after 31 days? So I want you to guess, right? Without doing the math, which one would you choose? Don't look ahead. There's no wrong answer. I just want you to guess, because this is helping you build your intuition for math. Okay, so let's look at option A, option B. All right, so option C, you get 30,000 on the spot, you're done. But if I look at, okay, how many days, and then how much money do I have? Ooh, okay, so look, under option B, what is that number? $21,474,836.48. Wow, what the heck? We started out with getting a penny. The next day we got 2 pennies, then 4, then 8 pennies, then 16. Alright, so we're really not making great money. Even on day 10, the amount of money we get in one day, that's not even minimum wage. Okay. So we're going to compare these 3. So the symbolic representation is a model for each situation. So A of T, remember, you start with $1,000 a day, then you start with $1,000 and then get an additional 1,000 per day. Right, so this is a linear function. Go ahead, write that down. Let's do C of T next. All right, so you get 30,000 on the spot. That is a constant function. You are done. But B, this is the equation, 0.01 times 2 to the t power, because this is an exponential function. Right, this is what the graphs of these would look like. You see the little orange is constant, so for over half the next month, this would be the best option, but it's because we had 31 days. All right, on the 31st day, you would make your 31st thousand if you had chose option A. Option C, you still have the same 30,000, and then option B, it just starts growing without bounds. So the domain, all of the domains are the same, right? 0 is less than or equal to t less than or equal to 31, because that's how many days we have. You start at the 0 day, you go to the 31st day. But the range, right, the y value, there's only one y value for option C, versus option A is between 1,000 and 32,000. But option B, remember, we start with 1 penny, but then we end up with over 21 million. So based on the option, after 31 days, you should probably choose B. But let's see why it grows so much faster. So let's just look at A and B. So notice between day 20 to 21, right, option A is growing by 1,000. Option B is going up by 10,000. Right, if we compare between the 23rd and 24th day, option A is going up by 1,000. Option B is going up by 83,000. What the heck? So in general, you can see the inputs increase from one day to another, right? So option A is going up by $1,000 a day, but B is doubling every single time. You're just doubling how much money you're getting every single time. In other words, A of T grows linearly because you're increasing by the same amount every single day, versus B is exponentially because it keeps doubling. So this is the big difference between linear and exponential functions. Outputs for linear functions change by addition, you just add the same number over and over again, versus exponentials are by multiplication. You're multiplying by the same number over and over again, doubling, tripling, etc. So you can tell if data is exponential by determining the rate of change, right? If you have a constant amount, constant ratio between y2 and y1, there would be exponential. So if I take 7 over 1.5, right, is that equal to 28 over 7? Is that equal to 112 over 28? Is that going to equal to 448 over 112? All of these have the same ratio, so this is going to be exponential. So what you can do is you can try example 5, pause the video. Alright, so when I see, is this going to be exponential? I see, okay, I am growing by the same ratio every single time by 5. And technically this is y to the 5x. So this grows by multiplication, versus the second example, right? We are growing, we're adding by 0.2. We're not multiplying by anything, we're adding. So the second one's going to be a linear, right? Because it's growing by addition. So if you pause, you can look at the numbers I wrote down. I can help you explain. Definitely as you go through the screencast, write your questions. Write out a list of questions. Where are you concerned? Where don't you understand? Also, ask each other for help. So exponential functions are in the form f of x equals a times b to the x. A is the initial value. B is the base, right? How much are you growing, decaying by, right? Are you doubling every time? Your base is 2. Tripling, right? Multiplying by 3 every time, your base is 3. So notice x is the input, f of x is the output. All right, it's literally a shape J with a intercept at 0, a, base b. All right, so it looks like a J because it just grows so fast exponentially. If the base is greater than 1, you have exponential growth and it increases from left to right. If your base is between 0 and 1, it's exponential decay, so it's going to be decreasing from left to right. So decreasing left to right versus increasing left to right. All right, cool. So you can always look at those. Here's some common ratios. So hopefully, give yourself a shot to try this out, especially A. Do you have a common ratio? Are you multiplying by the same number every single time? Okay, so 12 over 15, then 9.6 over 12, 7.68 over 9.6, etc., etc. Determine an exponential model. Okay, so we know how much we're multiplying by every single time, right? 4/5. We know our initial value, right? When x is 0, a is 15. So then you just write 15 times 4/5 to the x. Since this is between 0 and 1, you know it's going to be exponential decay. It's going to look like this, exponential decay. Determine f of 10, measure to the nearest hundredth. So you just put in 10 for your x, right? Because this is to the x. X is in your exponent, versus to the 50th. Ooh, right, as a decimal and in standard scientific notation. So I wrote the decimal first. If I count 1, 2, 3, move the decimal 4 times, this is just 2.14 times 10 to the negative 4. So scientific notation, you're expected to have learned in a previous class. This is what I'm talking about: exponential growth, exponential decay. So our initial value is this first one. You know, our base is the number here. Domain for exponentials are always all real numbers. They're always greater, the range is always greater than 0, right? Unless you flip it over the x-axis, right? You start with your range greater than 0. Horizontal intercept, there are none, right? You don't have a horizontal, you don't touch and cross the x-axis. It doesn't touch the x-axis at all. Vertical intercept, okay, this is when x equals 0. If I put in 0 for x, this just turns into 12 times 1.45 to the 0. 1.45 to the 0 is 1. 12 times 1 is just 12. Right? So we've gone over horizontal intercepts, vertical intercepts a bunch this year, so I'm not going to spend more time on it. Horizontal asymptote, so we're not crossing this line, right? It seems like when I'm drawing my exponential growth, there's this line I'm not crossing at the x-axis. Then you can see it's an increasing function, so you always can graph that. Okay, so this is what we already been talking about. Exponential functions are in the form b to the x, right? The exponent is your variable, b is constant. If the number is greater than 1, if you multiply by a number greater than 1 by itself over and over and over again, it's going to keep growing, right? If you take 2, times 2 is 4, times 2 is 8, times 2 is 16. It's going to grow bigger and bigger, bigger. Versus if you take a number between 0 and 1, so like 1/2. Well, half of a half is a fourth. Half of a fourth is 1/8. Half of an eighth is a 16th. This is exponential decay, right? Your piece of pie is getting smaller every single time. So the exponential function is an asymptote. So it's a line that the graph comes exceedingly close to but never touches. And it's like a freeway median. An electric fence or a railing at a Grand Canyon. You just don't cross it. You get really close, you just don't cross. Alright, so the asymptote for 2 to the x is at the x-axis, right? X-axis, just the horizontal asymptote. And then we plug in numbers for our x, right? Figure out what the y's would be. And then we have our points. Draw your graph. Don't cross the asymptote. Oops. Draw your graph. Don't cross the asymptote. The domain's all real numbers, but the range, it's all positive numbers, right? Notice there are no negative y values. So you're going from 0 to infinity, aka y is greater or equal to 0. Not equal, I'm sorry, just greater than. Right? Y can never equal 0. Transformations. So this is similar to what we've done in before. So if you were just subtracting 2 at the end, everything moves down by 2. Okay, so I could take my values that I just had for 2 to the x, subtract 2. Literally, this whole graph is just shifted down by 2. So I encourage you to pause the video, write all of this information down, see what is confusing. Right, the asymptote, well, it's no longer at x equals 0 or y equals 0. It's y equals -2 because even the asymptote was shifted down by 2. Right? We used to have an asymptote of y equals 0. Well, if you subtract 2 from that, now it's at y equals -2. Okay. The y-intercept is when x equals 0. So I plug in x equals 0, right here into the 0. 2 to the 0 is 1. 1 minus 2 is -1. Okay, so shift that down. And all of our values, you're just plugging in your x values. All right, this whole table, you're just plugging those in. All right, we've done tables before, you can do it. Domain is your x, it's all real numbers. Every x will give you a y value. But you don't have any y values that are less than -2. Versus, okay, so that was -2 at the end, versus if you have it in part of the exponent, this is horizontal. So if you would have absolute value of x minus 1, square root of x minus 1, you know, x minus 1 squared. Literally, horizontally, it's the opposite direction. So everything's being shifted to the right by 1. That's it. That's it. All right, all my values up here, shift them to the right by 1 value, and that's what my graph is going to be. Also, I know this might be a little confusing, so if that's confusing, you can just plug in numbers. So normally we go from, you know, -2 to 2 or something. Well, if we're shifting everything to the right by 1, I'll go -1 to 3. Right? You're looking at your transformations, and that's how you decide the values to plug in. Exponential decay, right? So you're getting smaller as you go left to right. And this is because your base is between 0 and 1. Notice we can't have a negative base because then it'd be flipping on either side. If I have a negative base, it's literally going to be flipping back and forth. So that's no bueno. No good. Alright, so once again, the asymptote, still the x-axis. Y-intercept, all you do, plug in x equals 0. Anything to the 0 power is 1. Most of your x-intercepts, y-intercepts, are going to be 0, 1. Awesome. Plug in a couple different x values. You get your y values, you plot your points, connect them. You see it's a decreasing function. You make sure not to cross the x-axis. Your domains all real numbers again. Right, your y values, it's still y is greater than 0. Okay, I think this is the last one. Perfect. So this is a difficult one. There's a lot of things going on, right? The negative in front is flipping it. The 4 is stretching. All right, the x to the -1, that's going right by 1, and then the +2 is going up by 2. Oh my gosh. So really the only thing that matters with asymptote is vertical translation. We are moving up by 2. Everything goes up by 2, including the asymptote. So draw the asymptote in green first. Y-intercept. Plug in 0 for x. See what number you get. Ooh, so 0, -6. This is just computation. And I think you can do basic algebra 1 computation for the y-intercept. Alright, so this part right here, plug in 0 for x and just solve for it. And then you want to plug in a couple values. You just want a couple points. That way you can connect them. All right, so if I would just have 1/2 to the x power, that would be decay. Right? If you just had 1/2 to the x power, this would be decay. But if you put a negative in front of it, okay, you flip it over the x-axis. So that's why this is flipped over, is because the negative sign in front. And then we stretched it by a factor of 4, right? So it's a lot steeper. And then we shifted up by 2, to the right by 1. So a lot of stuff going on. But notice the range. It's all these y values that are less than 2. Right? I have negative, really big negative y values, all the way up to 2. Cool. So that is the whole lesson for 7.1. If you have more questions, definitely watch some Khan Academy. Look at examples in the book. Come to bonus on Tuesday. Cool, because on Tuesday we're going to start the next lesson.